All right, chemists, here we go. Today we're taking a look at single replacement reactions. They're the last of our four types of redox reactions. The last type, double replacement reactions, we'll talk about more next time, but those are going to be involving Coulombic forces rather than the transfer of electrons. So let's dive on in. Now, single replacement reactions are among some of the neatest reactions in terms of the things that they can do. However, the description of them does sound a little bit confusing, but here it is. A single replacement reaction is a reaction in which a free element reacts with a compound in order to produce a new compound and a pure element that was originally in the original compound. Yep, that's confusing. So let's break it down. Let's take a look at an example. For example, the reaction I'm going to demonstrate in a moment is the reaction of aluminum metal with aqueous copper 2 sulfate to produce copper metal and aqueous aluminum sulfate. So we're starting with a free element. In this case, that is aluminum. Right here at the start of our reaction, we are reacting that with a compound, and it's going to be very important that this thing is aqueous because we need to react our free element with an ion, a separated ion. If they're still bound together in that crystal lattice, it's not going to react in any way. So we have a compound here. And as a result of this reaction, we're going to end up with a new compound where now aluminum is in that compound, and the metal that was originally in that compound, the copper, is now going to be in its elemental state. We're going to be forming copper metal out of this reaction when originally the copper was aqueous and dissolved. Simultaneously, we're going to be having aluminum metal at the start, solid aluminum, and at the end of this, we're not going to have any aluminum metal left. It's going to all be dissolved. We're dissolving one metal to recover another metal. Now, this is going to tie in some key ideas from earlier in the year. So some big things we want to bring back in case they may have slipped from our memory. Is first off, when metals react, they have to lose their electrons. So when we talk about metals being more reactive than each other, remember we're talking about their ability to lose those valence electrons. Metals that are more reactive will lose them easier. Metals that are less reactive have a greater attraction and tend to hold on to them a little bit more. It's also important to remember, as I already said, is that when ionic compounds dissolve, those cations and anions separate from each other. Right, so this allows the two ions to react independently of one another.
So to do this reaction, we first need aqueous copper 2 ions. So we're taking solid copper 2 sulfate here, we're dissolving it in some distilled water, getting it nice and warm. And in addition, we need to catalyze this reaction. So we do that by adding some chloride ions, and I'm doing this with just using sodium chloride from regular table salt. Then as we put aluminum foil in, you see that at the bottom of the edge of it there starts to rapidly react. As the aluminum metal replaces the copper ions, causing the copper to form back into copper metal, and the aluminum begins to dissolve. Because the aluminum foil is so thin, the reaction rapidly eats through it to the point that it becomes too brittle to maintain its form. If we used a thicker piece of aluminum, such as a bar or something, the copper would just be kind of coating the outside. But here we see the metal itself deteriorating as it dissolves away, and instead of plating the outside of the aluminum, the copper instead precipitates out to the bottom. But you can see the telltale reddish-brown color of the copper metal forming. Notice as the reaction is proceeding, the blue color of the solution is also beginning to fade from what it was at the beginning. This blue color is a result of the copper ions in the water, so as the copper ions are used up in the reaction, that blue color fades as well. And here we see just the remaining copper powder down at the bottom there.
Like I said before, this is a redox reaction. We do have a transfer of electrons here. It'll help explain a little bit about what's going on behind the scenes in the mechanism of this, and we'll look at a model of it in a moment to help clarify it even further. But if we look at the oxidation states of these, we know that all of our initial elements have a neutral oxidation state of 0. But our copper sulfate here, we have copper 2 sulfate. So that means that the copper is going to have that 2+ charge, sulfate's a 2-. That's what makes it electrically neutral. But at the end of this, we're forming a new compound, aluminum sulfate. Aluminum always reacts to an oxidation state of +3, and sulfate always goes to -2. So if we're looking at the changes that occur over the course of this, we have aluminum going from 0 to 3, so it's losing 3 electrons per aluminum, so that's being oxidized. Whereas our copper here is going from +2 in the initial compound to its elemental state, and its elemental state has an oxidation state of 0. So if it's gaining 2 electrons, then our copper is being reduced. So this is essentially a reaction where two metals are just trading electrons because one of them has a greater attraction for them than the other. All right, so let's take a look at some pictures, and that'll help break it down even further. Now here, we see in our model, we have our aluminum foil, right, represented by my amazing little model here of our aluminum atoms surrounded by the sea of electrons, because we know that metals are held together by these metallic bonds, right, the sea of electrons, as the electrons flow in between all those different aluminums. Now in my solution, I have some copper ions, and for whatever reason, my program made the little plus signs for my copper and my sodium ions go below them. Just ignore that. But I have my copper, I have some sulfate. I also have a little bit of Na plus and Cl minus here because we are using sodium chloride to catalyze this reaction. Notice it's not being used up in the reactants, it's not present in the products, it's just there to help get things going and reduce that activation energy. Right, so before anything reacts, this is the system we're looking at. We have all of these ions in the water, we see some water molecules as well. Now what happens to actually get this reaction going? Well, as those ions are floating around, some of these coppers are going to make their way to the surface of the aluminum metal. Right? They're just going to be floating around. They're free to move inside of the solution. It's just going to happen naturally over time. Now, what happens when they get close enough is that those copper ions that are floating around have a stronger attraction for that sea of electrons than the aluminum atoms in the metal do. So in essence, copper is going to be able to force out the aluminum, because copper here is going to attract and hold on to these electrons, which means that there's less stuff going to hold on to that aluminum 3+ ion, less things that are going to keep it there bound to the rest of the metal foil, the rest of the sheet. Now, because of the ratio of the charges of the ions, we are going to have a 3-to-2 relationship here, where we're going to be using up 2 aluminums and gaining 3 coppers out of it. Because of those charges, 3+ on the aluminum and 2+ on the copper. Now, as this happens, those copper ions that were free to float around the solution are no longer going to freely float around. They're going to be adhering and solidifying into that copper metal, the original aluminum foil. Right? The metal is plating on top of the other metal. So if you've ever heard of the phrase gold plating or metal plated, this is exactly what's happening here. That metal is forming a layer on the outside of the aluminum, right, as it continues to react and replace the aluminum that was in the foil. Right? And again, this is happening because aluminum is more reactive than copper. Remember when we said metals, when they react, they lose electrons. So if aluminum is more reactive than copper, aluminum is more easily able to lose those electrons. It's able to leave this solid state. Whereas copper, since it is less reactive, it has a greater attraction for those electrons, it's going to come and bind into this solid form. If we had enough copper ions and gave this reaction a long enough time, all of the copper in the solution would adhere to this aluminum, to the point where if we had more copper than aluminum, we could actually use up all of this and get rid of the aluminum foil, which is essentially what you saw in the video as the aluminum foil disintegrated and dissolved before our eyes. Now, just like the redox showed and how we talked about in the model a little bit, we know that we initially started with copper 2 sulfate, but the sulfate didn't really do anything. In fact, it just kind of stood there, and really it was just a reaction between the metal and the ions. So often what chemists use to represent these types of chemical reactions for single replacements and then double replacements when we get there are something called ionic equations. Now these types of equations, all they do is they take anything that's aqueous, right, dissolved in water, and they write it in the way that it actually exists in the system, right? In the beaker, in the containers, in the flasks. They write it as the separated individual ions. So if I have 3 copper sulfates, as my chemical equation shows, then I have 3 copper ions, and I also have 3 sulfate ions, which is what's being modeled here with 3 copper 2 pluses, because this is copper 2 sulfate, and I have 3 sulfate ions. Similarly, in my products, I know that I'm forming aqueous aluminum sulfate, and I have 2 aluminums and 3 sulfates in that formula. So here I have 2 aluminum 3 pluses and 3 sulfates. Now, for my solids, they didn't change at all because those are not aqueous or ionic. Those are just their normal metal elemental states. So those are just written exactly the same. And here, this really highlights now that the sulfate doesn't participate in the reaction. The sulfate is exactly the same in the reactant side and exactly the same in the product side. It doesn't do anything here. So what we call those when they don't participate, when they don't do anything, we call those spectator ions, right? Just like a spectator stands on the sidelines on the sport, they watch, they don't really participate, they don't play themselves. That's what these ions here are doing. They're just there. So really, they don't matter. In terms of what's changing, what's happening in the reaction, those spectators could be pretty much anything as long as they don't interfere with the reaction that's happening, because this here at the bottom is really the reaction that's happening. It is the only thing that matters. So that's usually what we call the net ionic equation, where we have the same ionic equation as before. However, we leave out all of the spectator ions. Now, as we do some net ionic equations, we can see that this, again, ties back to our redox, because if we take the sum of those 2 redox reactions, we get the net ionic equation. And so this is how everything starts to tie back together again. Here we see some more examples of net ionic equations, right, so that you have some examples to work with as you do some practice. Now, 2 things to take a note of is we said that anytime we have an aqueous ionic compound, it gets split apart. However, this also applies in some cases for different acids, because we know that most acids are aqueous. They're dissolved in water. For example, we can have hydrochloric acid, sulfuric, acetic. However, the only acids that are written as separated ions in an ionic equation are acids that completely dissociate, meaning every single molecule of that acid is a separated hydrogen ions and the anion. Things that are weak acids, they don't completely dissociate. Maybe 1 in a million molecules, 1 out of every 1,000. Right? There is some ratio there. Since not all of those dissociate, we do not split those ones up in ionic equations. So at the example number 3 there with acetic acid, we can see an example of that. We did talk earlier a couple weeks ago while we were on distance learning about the 6 strong acids. So look back at those examples, that reference sheet I told you to make at that time, so that you have those to reference and know which ones to split up out of the acids and which ones not to. So to sum up what we talked about with single replacement reactions, the big ideas are that the compound is going to need to be an aqueous ionic compound, right? It needs to have those free ions in order to be able to interact and replace with the other metals. There is no set rule for it being exothermic or endothermic. It depends on the reaction. In the video with my aluminum and copper sulfate, as long as we had that sodium chloride catalyst in there, you can see some of the steam rising off of the surface of the water. It is very exothermic as it's reacting there. And lastly, in order for a reaction to occur, the free element, our aluminum in this case, must be more reactive, right? Meaning it must be able to lose its electrons more than the ion that it is trying to replace. Right? This is why the reaction we saw actually happens, and it doesn't just reverse itself and undo itself. The aluminum is able to react and replace the copper. However, the copper is not able to react and replace the aluminum. Right? The reaction only occurs if the free element is more reactive than the metal it is replacing. Now, I keep saying metal here because that's the example we used. However, if the free element was a nonmetal, like chlorine or fluorine, it would need to replace the other nonmetal, right, the anion, because we couldn't put two cations together or two anions together. Those things would have to replace one another. So then the big lingering question is, how do you know which metal is more reactive? Well, to do that, we have to do some testing. We have to compare a bunch of different metals together and make what's called an activity series. And that's what we're going to do next.